sinusoidal modeling, or I like to call it applications of sine and cosine graphs, okay? Sine and cosine functions can be used to model a variety of real-world phenomena that are periodic. That is, they repeat in predictable patterns. The key to constructing or interpreting a sinusoidal model is understanding the physical meaning of the coefficients we've explored in the last three lessons. So sinusoidal model coefficients, again, sinusoidal curves or sine or cosine graphs, they come in the form y equals a sine of bx plus c, or absolute value of a is the amplitude, or the distance the sine curve rises and falls above the midline. The value of c is called the midline, or the average y value of the sinusoidal model. B is the frequency, which is related to the period p. The frequency is how many cycles you would see in a 2 pi interval. In the period is the length of a single cycle along the x-axis. And again, I use the formula period equals 2 pi over b. They have bp equals 2 pi. I use period equals 2 pi over b, just that form, as we saw in previous lessons. All right, so let's take a look at these problems and see how, setting up sine functions or cosine functions can, help us out here. So in the first one, it says the tides in a particular bay can be modeled with the equation of the form d equals a cosine of b of t plus c, where the letter t represents the number of hours since high tide, d represents the depth of water in the bay. So most of you are probably familiar with the fact that there's high tide and low tide, comes in and goes out twice a day, every day. This is a periodic function here. So our variable is t instead of the letter x, and instead of the letter y, we have the letter d here. But other than that, it's pretty similar to what we see above. And let's see, the maximum depth of the water is 36 feet. The minimum depth is 22 feet. And high tide is hit every 12 hours. On the axis, sketch a graph of this scenario for 2 full periods. Label the points on this curve that represent high tide and low tide. So look, it's a cosine curve, and it starts at its highest point, okay? The maximum depth of the water is 36 feet. So if you think about it, what do we know about a cosine curve, right? In general, a cosine curve has this shape to it. It starts up at its high point, hits its low point halfway through the period, and then ends back up at its high point. And here we have our midline. Okay, so we're going to have a graph that looks an awful lot like this, but we just need to account for the actual values. Okay, if I'm going to do a little rough sketch first, basically they're telling us that it's starting at high tide at 36 feet. So it's going to go out, it's going to come down and hit a minimum depth of 22 feet. So basically our graph is going to have this kind of a shape to it. Starts up at 36, comes down to 22, and goes back up to 36. The minimum depth is 22 feet. High tide is hit every 12 hours. That is giving us the period. It takes 12 hours to complete a single cycle of this cosine curve. Okay, and so that's basically what our graph is going to look like. Now, if we're going to go 2 complete cycles, as we've been asked to here, right, 2 full periods, we're going to go out to 24 hours, and we'll repeat this. All right. Now, let's find a couple of things. Let's figure out what the midline is. That's going to be the value of c. That's going to be the average of our y values. Okay, so I'm going to start with that. So the midline is going to be the average of high and low. Okay, so let's see, 36 and 22 is 58, divided by 2 is 29. So our midline is up at 29. Now we should be going both up and down by the same amount from there to get our amplitude. Let's see, if I go up 7, I get to 36. If I go down 7, I get to 22. So our amplitude is 7, and A itself is positive because we're starting up at the top of our curve as opposed to upside down. Okay, so we've got C and we've got A. Now we need the value of B. Okay, and again, period equals 2 pi over frequency. Well, we know the period. The period is 12 hours. So we can use that to solve for B. And it looks like we're getting pi over 6 for 12, for our value of B. So if I throw this all together, we're getting y equals 7 cosine pi over 6t plus 29. There's the equation, and now I'll graph it. So I'm going to call this 29 right here. We're going up to 36, down to 22. And let's see, one period takes 12 hours. So what's half of that? 6 hours. So that's when we'll be at our low point. And so every 3 hours, we're kind of counting by here. All right, so here's the first cycle of our cosine curve. Now I'm going to repeat that. Okay, I'm going to end at 24. Halfway in between those is 18. That's when I'll be at my low point, and that's going to give me 15 and 21 for the midlines. All right, and there we have it. Now, part C says tanker boats cannot be in the bay when the depth of the water is less than or equal to 25 feet. Set up an inequality and solve it graphically to determine all points in time t on the interval 0 to 24 when the tankers cannot be in the bay. Round to the nearest tenth of an hour. Okay, so can't be less than or equal to 25 feet. So that's going to be right about here. Okay, so I'm going to draw that horizontal line in. All right, so now we got some calculator work to do. Basically, we're looking, the water is below that depth from here to here and on this interval, on these two time intervals, okay? So look, let's go into y equals, and in y1, I'm going to do our trig equation here, 7 cosine pi over 6x, close the parenthesis, plus 29, and then in y2, I'm going to graph 25. All right, but before I graph, I want to make sure of a couple things. I'm going to go to mode, and I'm going to make sure I'm in radian mode. It's important that you're always in radian mode whenever you're dealing with pi's in a problem. And I'm going to set up my window. So my x min, it looks like, is going to go from 0 up to 24. And I'm counting by threes on my scale. And my y min, I'm gonna have a y min of 0, and I'm going to go up to, I guess I'll go up to 40, just a little higher than our max. And I'll leave, the tick marks. You can make whatever you want, mine are 5. Okay, but let's take a look at this graph now. And you should have a pretty good view of it if you set your window up like I did. Okay, and now once the line comes in, what we can do is we can use the intersect function 4 times to come up with these 4 values. So let's see, calc intersect. And I'm going to go left to right here. So just bear with me. The first one occurs at time. That's about 4.2 seconds right there. And the next one to the right of that occurs at about time 7.8 seconds. So between 4.2 hours and 7.8 hours, that's the first interval where the water depth is lower than 25 feet. And we'll get the second one now. So calc intersect. Okay, we're looking at about 16.2 for that value. And finally, 19.8. So that's the second interval. Between those hours, the tanker cannot be in the bay. And there we go. There you have it. Okay. So first example of a sine modeling, cosine modeling graph. All right, moving on. Number 2. The height of a yo-yo above the ground can be well modeled using the equation h of t equals, hold on, there seems to be a little lag in my screen here. Let's see what's going on. Okay, just give this a second, folks, while this is rebooting, and we'll get into it. Okay, hold on. For some reason, got disconnected. Okay, hopefully we're back in business here. All right, here we go. Okay, moving on to the second one. Okay, back to the yo-yo. Yo-yo goes up and down, repeats. It's like a sine or cosine function. Goes up, it goes down. The height of a yo-yo above the ground can be well modeled using the equation h equals 1.75 cosine of pi t plus 2.25, where h represents the height in feet above the ground, t the time in seconds since the yo-yo was first dropped from its maximum height. Determine the maximum and minimum heights that the yo-yo reaches. Show the calculation. So basically, we're looking for the range here. We could graph it all out, but I think easier than that, if we just work off the midline in the given amplitude, we can get that range pretty easily. So we have a midline of 2.25. From there, we know we're going to go up 1.75 as well as down 1.75. So, doing the math, it looks like we're going to have a maximum height of about 4 feet, that looks like. And a minimum height of 1.5 feet. Or no, half a foot. Okay, so its highest point is 4 feet, its lowest point is half a foot above the ground. How much time does it take for the yo-yo to return to the maximum height for the first time? In other words, what is the period? And this time we have b, that's pi, that's the letter in front of the variable in the parentheses. So our period is 2 pi divided by pi, which is just 2. 2 seconds on the nose. 1 second to go down, 1 second to come back up. All right, so pretty short and sweet question. If you wanted to, you could have graphed it. Really not necessary for this one. Okay, next up, a Ferris wheel is constructed such that a person gets on the wheel at its lowest point, 5 feet above the ground, reaches its highest point at 130 feet above the ground. The amount of time it takes to complete one full rotation is 8 minutes. The person's vertical position y can be modeled as a function of time in minutes since they boarded t by the equation y equals a cosine b of t plus c. Sketch a graph of a person's vertical position for one cycle and then determine the values of a, b, and c. Show the work to arrive at your answers. Okay, so look, the person gets on at its lowest point 5 feet above the ground. So let's keep that in mind when if we're doing a rough sketch of this thing. Okay, basically I'll set it up like this. Look, we're getting on at 5 feet, and we're gonna go up to our maximum height of 130 feet, and then we're gonna come back down. So the thing to notice is that, yeah, we do have a cosine graph, but it's upside down. So that's going to have an effect on the value of a here. Okay. But in any event, I've got that rough sketch on the side to work off of. Here's my midline C. I'm going to start with that again. So add the high and low values and take the average. So let's see, 135 divided by 2 is 67.5 feet. All right, it is what it is. Now, for the amplitude, how high up and down do we have to go off of that? So I'm going to do 67.5 minus 5 feet, and that's 62.5 feet for the amplitude. Okay, well, the absolute value of A is that. A itself, careful, is going to be negative because the graph is upside down. We're starting at the low point here. In terms of our frequency, let's see, the period is 8 minutes. One full rotation takes 8 minutes. So 8 minutes equals 2 pi over b. Multiply the b over and divide by 8. And it looks like pi over 4 is our frequency here. So the graph is going to become y equals, okay, negative 62.5 cosine of pi over 4t plus 67.5. There's the equation. And now we'll put it all together. So I'm going to call this 67.5 for my midline. Okay. Maximum is up at 130. Minimum is down at 5. And that's where we're starting. We're coming up. We're coming down. One full rotation took 8 minutes. Halfway would be 4 minutes. Halfway in between is where we hit the midline. So that would be 2 and 6. All right, folks, there it is. And last up, the possible hours of daylight in a given day is a function of the day of the year. In Poughkeepsie, New York, the minimum hours of daylight is 9 hours and the maximum hours of daylight is 15. If the hours of daylight can be modeled using a sinusoidal equation, what is the amplitude? Okay, so the maximum is 15, the minimum is 9. From that, we can get the midline, and that's going to be 24 over 2 is 12. So the midline's at 12 hours. And from 12, we got to go up and down how much to get to 9 and 15? Looks like 3 hours is our amplitude. All right, folks, give these last problems a try. Here are the solutions. Again, you may need to pause it to take a look. All right, folks, have a great day.